We are on day 22. You got page 14 in the packet. Remember to do that on a separate sheet of paper so you have enough space. We're going to keep looking at Taylor and Maclaurin series today. First one from the homework. We've got a power series. Notice it is just x to the n, so it's centered at 0. We know we converge at negative 2, and we diverge at x equals 5. So what I have there is a little picture of our smallest possible interval we could have and our largest possible interval. Smallest we could be is converging at negative 2, and then with an open circle at positive 2. Needs to be the same distance on either side from 0, but the endpoints could be included or not included. And then the biggest possible we could have, we know we're diverging at 5, so 5 can't be included. Well, hypothetically, we could have negative 5 be included on the other side. So the bottom is the biggest it could possibly be, the top is the smallest it could be, or it could be somewhere in the middle. So what's your smallest possible radius? Well, it would be 2. Your largest possible radius would be 5. And then for each of these values, we know for certain that negative 1, 0, and 1 are within that radius of convergence, because they're within even if it was the smallest scenario. So we know it converges there. We know negative 8 has to diverge because it's outside of the largest possible one. And then negative 5, 2, and 4, those are all in kind of the gray area. Bigger than our smallest, smaller than our biggest, so it could or could not converge there. All right, moving over to number 2. We'll do ratio tests so we can find our interval of convergence. So do limit of the absolute value as n approaches infinity of next term divided by current term. We get all but 1, 3 in the denominator to wipe out. All but 1 x plus 1 in the numerator to wipe out. And then I multiplied out my n plus 1 squared and wrote the n's over each other. Well, that's same degree, so ratio of the leading coefficient gives us 1 for that. We need that to stay less than 1 in order to converge. Do your negative 1 and 1 to get rid of the absolute value. Multiply by 3, subtract 1. So our initial interval of convergence is negative 4 to 2. We've got to test our endpoints, though, and we are subbing them into here. So when we put negative 4 in for x, we're going to get a negative 3 to the n. And when we put the 2 in for x, we'll get positive 3 to the n. So let's see what happens with each of those. So the negative 3 to the n over 3 to the n, that would simplify and just be a negative 1 to the n. Well, negative 1 to the n and negative 1 to the n, if you multiply those, that's just 1 to the n, which is 1. So you end up getting n squared. As n goes to infinity, that's not going to go to 0. So that one diverges by the nth term test. Pretty much the same idea with 2, just you'll end up still with the negative 1 to the n. So that's going to alternate, but the terms are still not going to go to 0. So that also diverges by the nth term test. So we don't include either endpoint in our interval. So when you have a derivative, remember the interval of convergence will be the same, possibly differing at the endpoints. So from our last one, if we multiply the exponent down front and then drop the exponent by 1, we get that series there. We know that it's got to be initially negative 4 to 2, and we just got to recheck the endpoints. So when you sub in the negative 4 and the 2, we again get negative 3 and 3 for our two options, but they're raised to the n minus 1 now. So I wrote the denominator of 3 to the n as 3 times 3 to the n minus 1, so that then the n minus 1's match up, and you've got negative 1 to the n minus 1. Well, if you've got negative 1 to the n and negative 1 to the n minus 1, no matter if you have an even or an odd value of n, you're always going to come back with a negative 1. So that's why that's just minus always. But still, as n approaches infinity, n is going to get huge on top, so that's going to diverge by the nth term test. And similar idea for the other one. You got the n cubed still left over on top. That'll diverge by nth term test. So our interval does not include either endpoint. So next up, we want to express this integral as a power series. So when you do the antiderivative of little f, you get capital F sub in x sub in -1. Well, subbing in -1 is going to give you -1 for x plus 1, which is going to be 0, and is going to wipe all that out. So this one goes away. So we've just got to represent capital F of x. So have your exponent go up 1 to n plus 1 and divide by n plus 1, and that represents your antiderivative of that original part that they had given us. We know our derivative and antiderivative will have the same interval of convergence, possibly differing at the endpoints. So that's why we can skip the ratio test and just take our answer from the previous part. So again, we're going to sub in -4 and 2. And the x spot will again have -3 for the first option and 3 for the second option. As we neaten things up, we're still going to get n squared over an n in both cases, so the top is going to grow bigger than the bottom, meaning it's still diverging by the nth term test. As a result, endpoints not included in our interval. Next one, we got to do ratio test, find the radius of convergence. So next term divided by current term. All but 1x minus 3 wipes out, that's left in the numerator. With our factorials, you'll have an n plus 1 left in the denominator, and you'll have 1 extra 2 in the denominator. As n goes to infinity, the denominator will get enormous. That's going to approach 0. 0 is always less than 1, so our radius will be infinite. If it asked for the interval, we would say -infinity to infinity. We want to use the third partial sum and approximate f of 4. So write out your first 3 terms by subbing in 0, 1, and 2. And we get that there. Sub in 4, you get either 5/8 or 0.625. We want to do our error. Well, notice we had an alternating series. So we would want to go to the next term. So we got to look at the fourth term, which is the one shown there. We were doing f of 4, so sub in your 4 for x. And it's the absolute value is your error. So we know our maximum error is 1/48. And if we want our error to be less than 10 to the -6, fill your 4 in for x. That's just going to give us 1 to the n on top, which is just 1. So we need to sub this in the calculator. Put your x's in for your n's and do a control T. We're looking for the first one that is less than 10 to the -6. That's the same as having point, then 5 zeros, and a 1. So 7 is still a little bit bigger, so 8's the first one that does that. So what we've just identified is the error term, because that's the next term. We want it, the error is the next term, we want it less than that 10 to the -6. So if the error term is 8, that means we want the one before, which is the 7th degree. So if we write our terms out until there's a 7th degree, then we'll be good. But always keep a lookout for where it started on the bottom. Now, if they asked for what value of n, we would just say 7. But they asked how many terms. And because we started at 0, when n's go from 0 to 7, we would actually have 8 terms. Sometimes that n on the bottom will be 1, so our answer would just be 7 terms. But here, because we started at 0, we have 8 terms. So we're not centered at 0, so we can't just use our memorized cos thing. So we want 3 terms, so we need the original and 2 derivatives. So we've got cos x, the derivative is negative sine x, second derivative is negative cos x. We'll evaluate each of those at -4 pi over 3, which is the same as being in the second quadrant with a 120. So you get your 3 derivative values there. So we start out with the negative 1/2, or sorry, not derivative values, because the first one's not a derivative, it's our actual function value. We start out with our function value, and then we have our first derivative times the x plus 4 pi over 3 to the first over 1 factorial. Then our second derivative, the x plus 4 pi over 3 to the second over 2 factorial, and then dot, 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 dot. They did not ask for the general term in number 4, so we did not have to write it. In 5, we want similar idea, but e to the x to the e. We want 3 terms, but this time we also have to write the general term. E's derivative nicely is e to the x for everything, so sub an e, you get e to the e for all of them. So this one was a little easier for the 3 terms. You got e to the e plus e to the e times x minus e to the first over 1 factorial. Similar idea for the third term. Well, our factorials go 0, 1, 2. Our powers of x go 0, 1, 2. So start with n equals 0. Just do e to the e, x minus e to the n over n factorial. Be really careful to look to see if they want a certain number of terms, if they want the general term. If they say to write the series, that means you've got to write the summation. So we're going to come up with a Maclaurin series. So that means our final answer should be a summation. We want 2x times e to the x squared. So we're going to start with our Maclaurin for e to the x, which e to the x has all of the powers and all of the factorials and everything's plus. Then we're going to sub in x squared, and that's what we have in the parentheses here. And then we're going to multiply by 2x. So we have this here. Notice our factorials go 0, 1, 2, 3, 4, and so on. So we have n factorial on the bottom, starting with n equals 0. Everything has a 2, so just put your 2 out front. And then the x powers go 1, 3, 5, 7, 9. So think of that as jumping by 2, so we need a 2 as our coefficient of n. But when you sub in 0, 2n is 0, and we want 1, so you need a plus 1 as well. The second way we're going to do it is we're going to differentiate e to the x squared, because e to the x squared's derivative should be e to the x squared times 2x. So this bracket here was our e to the x squared. Well, that first term is really 1. 1's derivative is 0. The second term, multiply the 2 out front, you got 2x over 1 factorial, and so on. Do the derivatives for each of the others. Well, if we now look at our values, if we were doing n equals 0 again, our factorials are 1 more than our terms. So we need n plus 1 factorial down on the bottom. So we have multiples of 2 out front. So 2 is really 2 times 1. 4 is really 2 times 2. 6 is really 2 times 3, so it's 2 times 1 more than the term we're with. So that's where the 2 times n plus 1 comes from. And then our powers, we have the 2n plus 1 again. We had the same powers as before. Now, are those the same? Well, notice if you divide an n plus 1 out of both the top and the bottom, you end up with just an n factorial on the bottom, so yes, they do end up as the same. So in our series that's written there, remember we'll always have an x to the n over n factorial. So that means that other part must be the nth derivative that we're working with. So we want the fourth derivative at 0. So we can just sub in 4 for n, and that gives us 80. And that can work for any derivatives at 0. In B, you can't determine the fourth derivative at 1 because this series is centered at 0. So it can tell us the derivatives at 0, but not at other values. Coefficient of the 12th degree term from Maclaurin for cos. Start with our basic cos. Nothing in there that says we have to write the general series, so we won't bother with that. Sub in x cubed. After you sub in x cubed, you see that third term is a 12th degree, so that's 1 over 4 factorial, which is the same as 1/24. In 9, notice we want a Taylor series, so we got to make sure we have the general summation for our answer. Start with our general cos, sub in an x squared. That's in the second line. Now, I personally like to build the general series as we're going, so that's why with that general cos, notice we have our factorials are twice whatever the term is when we're starting with 0, and the exponent just matches that, and you have a -1 to the n because we want it to go positive than negative. Then I think it makes it easier because when you sub in the x squared, just put x squared in your general series and you get x to the 4n. And then we want to do the antiderivative. Don't forget your plus c. We usually put that in the front with these. So you'll have c plus x. And notice all of our exponents are going up 1, and we're dividing out front by the new exponent. And that happens in our general series too. Exponent went up to 4n plus 1, divide by 4n plus 1 out front. And I just like to check a couple terms. So for example, when n is equal to 1, we should have this here. Well, -1 to the 1 is a negative. We'll have 4 times 1, which is 4, plus 5, so we get 5 in both these spots, and 2 times 1 is 2 factorial. So I think it's helpful just to check, because sometimes when things like neaten up and simplify in the front end, you could have to make an adjustment with the n equals under your summation sign. E to the x over x, start with e to the x. That's all of our exponents, all the factorials, and it's positive. So our general form starting at n equals 0, we have x to n over n factorial. Because we want a Taylor series, our final answer should be some type of summation. If we put everything over x, notice in our general term now we're x to the n minus 1. We want to do the antiderivative. So we will have a c plus 1 over x is natural log absolute value of x. This is just x. Here we have x squared and then a 1/2 out front. So here's an example of one where you have to be a little bit careful. So if you do just this antiderivative, you do get this. You get x to the n over n times n factorial. But in addition to our c, this ln absolute value of x didn't really follow that pattern. So we want to start here with our summation, and that would be with n equals 1. So this is a good example of one where it's helpful to have a couple of terms written out so you can make sure that bottom number on the summation is accurate, matching our series. So from our cos x squared, we had that thing on the right from question 9. When you sub in 1 and sub in 0, the zeros wipe out everything. They wanted us to use at least 3 terms, and the c's we ignore because those are going to wipe out. And for that, we get 977 over 1080, or out to 3 decimal places. It is alternating. So for our next term, we would want to go to our 13th degree term. So sub in 1, and we get 1 over 9,360. So we want e to the negative x as a Taylor series. That means we should have an actual summation. So start with your e to the x. And then with negative x, we'll just add to it a -1 to the n out front. For your antiderivative, notice we're at n plus 1, divide by n plus 1 out front. Don't forget your c plus. Now to evaluate from 2 or from 0 to 2, the zeros are going to wipe everything out, the c's will wipe out, and they want us to use at least 3 terms. So here's our 3 non-constant terms. Sub in your 2, and you end up getting 4/3. Use the next term, because it's an alternating series, to find the error. So that's our 4th degree term, and we get 2/3. All right, so today we're going to look at using our Taylor series and manipulating them algebraically to get new series. So we're going to work at x equals 2. So because that's our center, notice this is not a Maclaurin. That represents all of our derivatives. And our initial value at 2 we said was 4. So we want at least our first 4 terms. So f of x, we're going to start with 4. And then we're going to need our first derivative. So if we sub in 1 here, 1 squared is 1, minus 2 is negative 1. 3 to the first is 3. So our first derivative at 2 is going to be negative 1/3. If we want 4 terms, we're going to have to get out to the third derivative term. So let's maybe just go and do those all right now. So if we sub in 2 for n, because it's the second derivative, we'll have 2 squared is 4, minus 2 is 2. 3 squared is 9, so we get 2/9. And our third derivative at 2, if we sub in 3, we'll get 9 minus 2 is 7. 3 to the third is 27, so we'll get 7/27. Those will each be out front. So the next one, we're going to have negative 1/3. We're going to have x minus 2 is raised to the first over 1 factorial. You don't have to write the raised to the first and 1 factorial, but just so you can see the pattern, I want to write it for you. And we'll have plus 2/9. We'll have x minus 2 now to the second over 2 factorial. Then we'll have plus 7/27 times x minus 2 to the third over 3 factorial plus dot, 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 dot. Well, now we want to find the interval of convergence. So we need to start out and write what our general series is for f of x. Well, we're going from n equals 0 to infinity. Our general form of our derivative, they told us, was n squared minus 2 over 3 to the n. And we've always got our x minus 2 raised to the n over n factorial. So we're going to do our ratio test. We'll do limit as n approaches infinity. We got to do our next term divided by our current term. So for our next term, we'll put in n plus 1s everywhere. This will give us n plus 1 squared minus 2 over 3 to the n plus 1. Then we'll have x minus 2 to the n plus 1 over n plus 1 factorial. Times the current term, or divided by the current term, so we'll do keep, change, flip. So on top now we'll have 3 to the n times n factorial. And on bottom we'll have n squared minus 2 times x minus 2 to the n. So that will equal limit as n approaches infinity. Absolute value of, well, let's see, we're going to have, for our 3's, we'll have 1 extra 3 in the denominator. So that'll take care of those. For our x minus 2's, we're going to have 1 extra in the numerator. And then for our factorials, that's going to be gone, and this will now just be an n plus 1. So we've got to multiply out the n plus 1 and the n squared minus 2, and we've got to do this out as well. So n plus 1 squared is going to be n squared plus 2n plus 1. So when you subtract the 2, you'll have n squared plus 2n minus 1. When you multiply out the n plus 1 and the n squared, you're going to get an n cubed. We'll end up with an n squared, a minus 2n, and a minus 2. Well, notice our powers of n are greater on the bottom. So as n goes to infinity, this is just going to equal 0, which is always less than 1. So this is going to converge for all x. So therefore, our interval of convergence is just going to be from negative infinity to infinity. If they had asked for the radius of our interval of convergence, we would say infinity, but interval negative infinity to infinity. So next we're going to work with taking something we know and building on that to get new things. So earlier in the unit, we said that 1 over 1 minus x is like a geometric where your first term is 1, the a1 on top, and you're multiplying by x over and over again. So that's the same as this series here, 1 plus x squared, and in other words, that's x to the n. But we're going to use that to find a series for 1 over 1 plus x. Well, that's just with a negative x subbed in here. So we're going to take our series, we'll have 1, we'll have minus x. If you do negative x squared, you're going to get plus x squared. If you do negative x cubed, you're going to get minus x cubed, plus dot, 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 dot. And if we do our general series, we're still going to have the x to the n, but then we'll also just have a negative 1 that's being raised to the n as well. Because essentially we had negative x to the n, so then I just split those up separately. Well, let's see if we can use that to now find a series for 1 over 1 plus x squared. And just to keep track, they had called this g of x, because they're now calling this one h of x. So we can take our g of x and replace all the x's with x squared. So if we write out our terms, we had 1 to start. In g of x, we had minus x. So that now replace the x with x squared, you get minus x squared. Then we had plus x squared. Well, if you replace that with x squared squared will become x to the 4th. Well, next we had minus x cubed. If you replace x with an x squared, we'll get minus x to the 6th, plus dot, dot, dot. We had an x squared that we put in. We had x to the n in the general term. So now we're going to have negative 1 to the n, but x will be to the 2n. Moving down to the bottom, we're going to use what we had in h of x to find a series for arctan. Because 1 over 1 plus x squared's antiderivative is just arctan. So for j of x, which is what they want us to call this, let's do our antiderivative of the series above. Let's first write out the terms. When we do an antiderivative of a series, we'll usually put the c first, so it doesn't get caught in the dot, dot, dot. So we'll have c plus antiderivative of 1 from above is x. Antiderivative of x squared, negative x squared will be negative 1/3 x cubed. Then we'll have plus 1/5 x to the 5th minus 1/7 x to the 7th plus dot, 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 dot. Keep in mind before in h of x, we had n equals 0 to infinity. We had negative 1 to the n, and we have x to the 2n. So if we think about doing an antiderivative there, we should have x to the 2n plus 1 now. We'll still have negative 1 to the n, and we have over a 2n plus 1 now. We've got our summation, n equals 0 to infinity, and just make sure you have your c plus out front then. It's good to check a couple terms. When we put in 0, we should get a positive. We'll have x to the 1st, and it's over 1. And that does seem to match up. Well, we're going to use this now to evaluate a limit. We want to find this limit. Well, this is the same as the limit, or I guess I should say, let's write our expression first. This is the limit as x approaches 0. If we take our arctan, oh, I guess let's go back one thing I forgot to mention. When you have a c, if it is something that you know some values of, see if you can resolve the c. In this case, we do know some values of arctan. One thing we know is that arctan of 0 is equal to 0. So in this series, when we put in 0 for j of x and put in 0 for all the x's, we should get back 0. So that tells us that c should be 0. So in this one, we actually can resolve the c. So really, j of x is just going to be x minus 1/3 x cubed, dot, 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 and we'll just have it without the c. Now, not all of the functions we have, we will be able to find a nice thing for to allow us to resolve the c, but if it is something we know, we should try and resolve it. So going back down to the bottom, so we want to divide all of these things by x. If we divide them all by x, x divided by x is 1. The x cubed divided by x will now give us negative 1/3 x squared. The x to the 5th, which was the next one, divided by x will give us plus 1/5 x to the 4th, and so on. Well, as x goes to 0, this is just going to approach 1. And we're going to look at one more limit to finish out the class. So we're going to use series to evaluate this. So we're going to start with our sin x Taylor series. Sine, remember, is odd, so we should have all the odd powers and factorials, and we'll switch signs. So we're going to have x, which is really over 1 factorial. It's up to you if you want to write the 1 factorial, minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus dot, 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 dot. Now, it doesn't say anything in here that we have to actually write what the series is. We've just got to use it, so we don't necessarily need to write the general term. So next we'll do sin x minus x. Well, if we take what we have on the right, x over 1 factorial is the same as saying x. So when we subtract x, that one's just now gone. So we'll now just have minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And I'll write one more now, minus x to the 7th over 7 factorial plus dot, 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 dot. Now we want to write out what sin x minus x over x cubed is. So we're going to divide everything by an x cubed. So this will become minus 1 over 3 factorial plus x squared over 5 factorial minus x to the 4th over 7 factorial plus dot, 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 dot. Well, now we've got the expression that we want to do the limit of. So for our limit, as x approaches 0, of sin x minus x over x cubed, if we look at this here, we're just going to have minus 1 over 3 factorial, and then everything else is going to be zeros. So this is just going to give us negative 1 over 6 for that limit. So start with something we know, like the sin x Taylor. Build it from there, adding, subtracting, dividing to get what the expression is we want, and then do the limit. That's it for today's video. Have a great rest of your day.